Hello, and thank you for joining us. This is Getting Started with Cosmos DB. It's the first of a three-part series to help you build high-performance apps using Cosmos DB. Today, Sri Ram is going to take you through an overview of common use cases and solution architectures and walk through the basics of how to get started. In the description area of this video, you'll find links to hands-on exercises, code samples, and other resources. And with that, I'll hand it over to you, Sri.
Hi guys, my name is Sriram. I'm one of the principal cloud solution architects at Microsoft. Today I'm going to talk to you about Azure Cosmos DB, a fast NoSQL database, and what are the use cases that this database solves. We also see cutting edge architectures, customer use cases, and also you will find a lab in the links so that you can try all of this yourself. Let's go and see what a NoSQL database is. A little bit of history. If you started your IT journey in 1980s and early 1990s, most of us would have started our journey with relational world, and SQL Server is one such a relational database wherein we have a lot of entities which are tables and the relationships between the entities and the columns, and everyone knows what a relational database is, and to this day they are very popular databases. And as you can see, a relational database comes with entity relationships. As you can see, the entities are related. There are primary foreign key relationships. There are one-to-one relationships, one-to-many, many-to-many relationships. And all of this, when they are interacting with the front-end applications, have an impedance mismatch. So front-end applications need a relational mapper in order to overcome this impedance mismatch. As you can see here, inside a relational SQL database, authors and ISBN and price might be represented in certain way. However, in object databases, they can be represented all at one shot as an object. And the first such attempt was made in 1990s. And as some of you could remember, this came as a derivative of RDB, but the only thing is these databases never took off. Then an amazing thing happened in 2000s. The internet happened, and with the internet, a lot of companies like Netflix, Amazon, they revolutionized the way that they deliver the content, they perform e-commerce and so on. So the relational databases gained much more strength because a lot of data need to be stored, and that's where the data revolution started. And also, we started thinking about cloud scale economics. So why should we think about cloud scale economics? As many of you know, in cloud, we do scale out versus scale up. You can only scale up to a certain extent, post which you will exhaust all the resources. So as the internet companies started storing lots and lots of data, then we actually reached the limitations of a single server. You can only scale up to a certain extent. So therefore, we needed a scale out architecture, which was not possible with relational databases. And here is where NoSQL databases came into light. So as you can imagine, in the NoSQL database, we actually don't create references pretty much, like entity relationships, and we actually won't have primary key, foreign key relationships, and I will talk all about it in a minute. Uh, so let us actually see how this whole NoSQL journey started. So the story goes in 2010s, in a meetup, the word NoSQL is coined up without actually paying too much attention, other than for the fact that it's not only SQL. And today, NoSQL databases have many characteristics. And some of those characteristics are they are non-relational in nature, they have scale out, and they are schemaless. So these things are all born out of the desire to address all these new needs of the internet world, namely the ability for the applications to cache key value pairs in the memory a lot faster. So they need to have a sub-second read and sub-second write response times for such a key value databases in order for the web applications to work properly. At the same time, instead of storing all the related data in the form of rows, we can store them as column families. There are yet these class of databases where we should store documents which are nothing but JSON elements as objects. That eliminates the need of object relational mappers. And there are these graph databases that determines the linkages or the relationships between complex entities. And we will come to all of these at a greater detail later on in this session. But all of these are the valid use cases where a SQL database struggled to perform. And therefore, we needed a new class of databases to serve these multi-model scenarios. So the NoSQL arrived, and people thought about all of these scenarios, and they coined the term NoSQL. So as part of NoSQL, some of the very important things happened, especially at Microsoft. So Microsoft started NoSQL journey with Project Florence in 2010. And we branded it as Azure Document DB in 2015. And then in 2017, we rebranded it as Azure Cosmos DB. So Azure Cosmos DB is rebranded as a multi-model API store. So Cosmos DB, what we know today, is a true NoSQL, but more than a NoSQL database, it is also a multi-model API database. So which means we provide you the ability to store your documents, to store your column families, to perform the graph computations, and also cache your key value pairs, all in one database. As you all know, modern life is completely app-centric. Everything is an app in our life. Without apps, we cannot pretty much do anything in our life. All the facets in our life are tied to apps. And today we are going to see how Cosmos DB is going to solve the use cases in areas of app development. Guess what? Apps run on data. And they not only run on any kinds of data, they need real-time data in order for them to provide the best class user experience. At the same time, as developers, we all have new requirements. We have cutting-edge editors. We have many needs from the users to meet their low response times, to provide the high availability of these applications across the world, and provide potentially unlimited storage scenarios. How do, as developers, we cater to all these brand new requirements? So modern app, as you know, could be coded in many programming languages. Today, people use Python, Node.js, C Sharp, Java, and many other programming languages. And we need a modern database to cater to modern programming language. So let's talk about how Cosmos DB helps you in order to overcome all the challenges that I have mentioned. So in order to overcome these challenges, at minimum, you need following four things. You need low read and low write latencies, and those latencies should be guaranteed, and you should get them consistently. This is where guaranteed speed at any scale comes into picture. And also, you eliminate ORMs in the middle and therefore directly interface with the database from your programming language, thus simplifying your app development. Your application should be mission critical, and therefore, if you were to occur a region outage, your application has to immediately be available in a backup region and with similar latency. So we'll see how we can solve the mission critical readiness with Cosmos DB. Cosmos DB also is fully managed, and that eliminates the need as a developer or as an administrator for you not to worry about the infrastructure, but to worry about how you can properly design your database and properly develop with your new database and leave management to Microsoft. At the same time, you got to get utmost cost effectiveness while we manage this database. And we will see how you achieve the cost effectiveness with Cosmos DB very soon. Today, I'm going to talk about three different customer use cases where Azure Cosmos DB powers real-time applications anywhere in the world. The first is in the area of IoT device telemetry. I will show you the demo of I'll show you the demo of an application wherein IoT device telemetry is ingested and we build a real-time application on top of that. And also over next 2 weeks, we will see what are the best practices of performing such an IoT device ingestion and how Cosmos DB is suitable to deal with the use case of IoT device telemetry. We'll also see the use case of personalization and recommendation, wherein a large retailer who actually is in the fashion industry performs personalization and recommendations all from Cosmos DB. So this is a use case wherein Cosmos DB could not only be used for operational needs, but also for analytical needs. Yet there is the third component wherein we will see how we have solved global and mission critical readiness for one of our customers, wherein they can deploy mission critical apps all across the globe in a mission critical environment. Let's see an example of Mercedes-Benz. So everyone knows about Mercedes-Benz. I own myself a Mercedes-Benz. It's one of the greatest vehicles that we could travel in. And guess what? It is not only a great machine, but also a great machine with best-in-class electronics. And best-in-class electronics need best-in-class deployments. And let's see how Mercedes-Benz have created a cloud-native IoT solution in order to actually improvise the in-car digital experiences so that they don't need to wait months long um, to provide the new experiences to the end users, but can deploy the software onto the car very frequently while providing geo-redundancy, high availability, low latencies, and how Cosmos DB provided the key role in their journey. Here is the testament from Mercedes-Benz Research and Development of how their software process is so much better now and how they are able to release the software inside the cars in weeks instead of months while preserving the quality and the end user and the end user experience. Here is a sample architecture of real-time telemetry ingestion. So in the real-time telemetry ingestion scenario, you have devices on the left-hand side, and all the devices will be pumping the data to a cloud gateway. In this case, the cloud gateway is Azure IoT Hub, from which a Spark application performs a real-time streaming, and the data hence streamed is ingested into Azure Cosmos DB, which in this case is acting as a hot storage. And then from Azure Cosmos DB, we can write Azure functions to move the data to the cold storage later on to perform analytics on top of that. And the analytics could be performed on Azure Synapse, which is our enterprise serving layer, and cloud native data warehouse. And you can actually render all the analytics in form of dashboards. So this is an example of how you can actually use Azure Cosmos DB as a centralized database wherein it performs with modern techniques, modern microservice techniques such as Azure functions, and also it performs with cutting edge technologies like Databricks Spark, and last but not least could ingest high volumes of data from your IoT devices. Now let's see the use case of ASOS. ASOS is a fashion company, right? So they actually discover fashion online. That's their logo, and they need to perform real-time product recommendations for 15 million plus global customers. And as you can imagine, when you are providing recommendations to your end users at such a scale, your database need to have a millisecond latency in forms of reads and writes. And this application is global because this is a global company. Everyone should be able to access their data with same guaranteed low read and write latency. And this database should be scalable for many, many more global customers. And then we use microservices in this particular example, and I will describe in detail of what the role of microservices is in order workflows. So as most of you know, when someone is performing an order, you first add an item to the cart, and then you revisit the item, let's say after adding 3 more items, and you decide you don't want the item anymore, you remove the item, and then you check out and you complete the process. So therefore, order workflows are very complex. Though they operate as independent microservices, the ability for them to communicate each other and to process in certain order is very important. And this is where change feed of Cosmos DB comes handy, and we will see that as we go. So here is actually Cosmos DB scenario in ASOS, where it was able to handle heavy seasonal buzz, especially as you know, during Black Friday, Christmas, and New Year's. A lot of people probably would be buying much more than during other periods of the year. And therefore, our database should be able to handle heavy seasonal buzz. Let's see the sample architecture of how we could implement a real-time recommendation engine with microservices architecture. As you know, Azure Service Fabric is a microservices engine. And in this case, let's say shoppers shop from .com page, and we orchestrate everything in microservices, wherein microservices interact with Cosmos DB. And then from Cosmos DB, we could take the data to the offline raw data storage, such as enterprise data lake, for longer term storage needs. But also we can take all the data that is coming in near real time into the analytics layer through our high capacity ingestion framework, uh, the PubSub framework called Azure Event Hub. And once all the data are there in the data lake storage, we can write cutting edge machine learning algorithms in order to create a recommendation engine. And once the model is deployed, the real time scoring against the recommendation model could later be stored back into Cosmos DB and could later be served to your shoppers. So all of this is cyclical in nature, so that you start from .com page and you end everything with .com page. And the idea is we need to provide a millisecond read-write response while all of this is happening in the back end, utilizing the microservices. And this is a sample architecture for such a Lambda architecture. And let's talk about our third use case, the Coca-Cola, wherein Coca-Cola have lots of bottlers all across the world, and they serve so much beverage across whole world every single day. And now they want to gather the sales revenue data as it occurs across the world, right, in minutes versus waiting for such a data set for, let's say, days. So they used Cosmos DB in order to achieve this. As you can see from the testimonial here, Coca-Cola was able to scale and generate insights within minutes versus days. And how could such an architecture look like? What we spoke about some time back is Azure Cosmos DB being a globally distributed database, and it can solve mission critical needs. As you can see here, your end application passes through Azure Traffic Manager, and Cosmos DB is deployed across various regions. You can perform multi-region reads and multi-region writes. And on the back end, the Cosmos DB is able to serve the requests all across the world and with the same latency of less than 10 milliseconds. So now, after seeing all of these use cases, let's summarize what exactly we have seen in all of these use cases thus far. We saw we can guarantee the speed of less than 10 milliseconds at any scale. We saw this database is mission critical and it is available across the world. And you can perform multi-region reads and multi-region writes in order to ensure the mission criticalness. And also in a minute, we will be seeing how we can actually perform the app development using several APIs and SDKs and what we should be doing in order to achieve the simplified app development. And last but not least, it's a fully managed platform as a service solution. So moving on to app development, we offer 5 different APIs. We offer a core API, which we call SQL API, wherein if you are starting your developments brand new, you will be actually spinning up your Cosmos DB account with core API. We also know that many of you have been running large installations in form of MongoDB and Apache Cassandra or DataStax Cassandra on-prem. And if you want to actually migrate your MongoDBs or Cassandras into the cloud, you can actually migrate with a mere change of connection string in form of Cosmos DB Mongo API and Cosmos DB Cassandra API. And also we provide you the ability to load your graph-like databases in Apache Gremlin API called Graph API. And then the table API, if you guys are familiar with Azure Storage, and in Azure Storage there is a table. But if you want to take the table to the next level, wherein you take advantage of all the goodness of Cosmos in perspective with global distribution and getting millisecond read-write latencies, then you can actually use the table API in Cosmos. So just let's summarize the mission critical readiness. Azure Cosmos DB delivers zero downtime with zero RPOs because it can be distributable, and we can actually use Traffic Manager to migrate our traffic to the nearest Cosmos DB location. Cosmos DB comes inbuilt with multi-master writes. With a single click of button, you can actually write across different regions. And we have enterprise-grade security in form of encryption and self-managed keys. And also, it comes up with RBAC, wherein you can keep your data safe. So coming to the fully managed service, we manage your database so that you can take your database all the way from 10 gigabytes, let's say, to hundreds of petabytes. Also, we provide the compute in order for you to fetch the data from your storage. So we offer different strategies for you to perform the scaling. You can have provision throughput. You can, within the provision throughput, you can do it in a manual way, or you can set up auto scaling. And also we introduced a serverless component very recently into the mix, wherein you can use our cost-effective serverless scaling for your development and small workloads. So now coming to the migration scenarios of Cosmos DB database. So let's make data modernization easy with seamless migration, aka changing the connection string. We actually offer Azure Cosmos DB Mongo API, like I said, Cassandra, wherein you can bring your on-prem workloads into the cloud, and we manage the infrastructure and virtual machines that are needed to run your environment. So let's see a customer use case in form of Norton, where they migrated their on-prem Cassandra into the cloud, wherein they migrated the massive amounts of data into the Cosmos DB API, Cassandra API, so that you can see the volume of requests here. They protect 40 million endpoints in 150 plus countries, and they receive 15 billion requests per day. And the column family database is lifted and shifted into the cloud into Cosmos DB Cassandra API, and they get similar experience right out of Cosmos. So this is a success story of migration from Cassandra API, from Cassandra on-prem to Cassandra API in the Cosmos. So today we are going to see about Contoso Logistics, a fictional customer who actually performs vehicle delivery to the customers. So wherein they actually take, let's say, the loads or packages or consignments all the way from one customer to other customers, or customer to the shelf, let's call it. So that is our company. We will see how Contoso Logistics looks like. What we do is we track vehicle and delivery status in near real time. We ingest ground vehicle telemetry at an extremely high rate. so that we have actually the ability such as tracking the temperature of the packages, or if the driver is speeding the vehicle. And we ingest actually all the data regarding the shipments and the ability for us to track their shipments all the way from pickup to completeness. So we build a web app to see the status of these vehicles, consignments, and packages. And this web app is built on Cosmos DB. So let's see the very simplified architecture, which definitely we will expand on in coming slides and coming weeks. But for now, think of Contoso logistics is nothing but it tracks the vehicles right from package pickup all the way to the completeness of the consignment. So this is very write heavy because we have to ingest massive amounts of vehicle telemetry from all the different vehicles we have. And once we get that into the cloud through the cloud gateway called IoT Hub, then we do microservices architecture to perform the event processing and store the data into the Cosmos. And on top of that, we have a web app in the form of a read-heavy application wherein our fleet managers log into the web app and see all different vehicle uh, telemetry and the information. So let's go ahead and see our first demo in form of Contoso Logistics. So as you can see here, this is our home page and this is our fleet management site. This is deployed as a web app, which is running on Azure and hosted on Azure App Service. And it has these simple screens wherein you can manage your vehicles, you can view your consignments, and you can view the trips. First, let's see how we can manage our vehicles. As we can see here, we actually got so many vehicles in our fleet. So for example, if you want to see the details about any particular vehicle, you go to the VIN number and you see the details pertaining to that vehicle. And you can also see such things as predict battery failure, wherein I can perform a real-time prediction of if my battery would be failed. And also, we actually have a nicer view or a consolidated view of our trips on the right-hand side, wherein this particular trip is currently in pending status and what should be the temperature that needs to be maintained, and when the trip is created and when the trip ends, if the trip ended, and who is the customer for that trip and whatnot. So then you can always edit the vehicle from here and make any adjustments or changes to that. You can actually see the different consignments. So for example, let's go ahead and see this consignment. And in this consignment, you see this is still in pending status, and you can actually see the packages and the statistics of those packages. And then last but not least, a very important view today we will be seeing is the trips view, wherein we have the relationship established between vehicles, consignments, and the number of packages in each consignment, and the trip distance, and if the trip is started or not, and if the trip is finished or not, and all other details could be viewed from here. And this is a simple application, but nevertheless, it shows you how someone can actually visualize all the data and perform the CRUD operations against our backend database in form of Cosmos DB. So let's go and see how we can actually create such a web application using this very high level architecture. Moving on to the next slide. We saw the vehicles. And then why Cosmos DB? One of the let's revisit the requirements of this project. In order for us to build the app, we need to have a flexible schema. Think about the sensors and think about the data that sensors pump to our application. The sensor data can always change over time because someone can always upgrade the sensor very frequently. A sensor may not belong to the same company. Different companies will have different metrics that they can track. All of the metrics might not be the same. All of the data that come from these sensors might not be the same. And therefore, we cannot say for sure that the schema is 100% fixed. This schema can be flexible. And it is bound to be flexible because of the Internet of Things kind of ingestion. And therefore, we need a database that has the flexible schema associated with that. Okay, we check mark the number one property of a NoSQL database. Then we need this to be scalable, especially for the rides, because we get a lot of data from each vehicle. And let's say in every minute we get a couple of data points from each refrigeration unit within your truck. And last but not least, from the sensors that are built on the truck itself, they all add up to be lots of data points, which turns out into high number of writes per second. And therefore, we need the database to be scalable. And we need the database to be to perform extremely fast under read scenarios. We can provide bad experience to our fleet managers. They should be able to read the status quo at a very fast pace to make a very real-time decisions, and therefore it has to be very fast. And also, it needs to be highly available, because we have operations all over the US. Just in case if we have a region outage in US West, let's say we need to have US East up and running, and all of our traffic should be diverted into US East. Let's see some of the some of the pillars of Azure Cosmos DB. Azure Cosmos DB resource model looks like this. At a very high level, you have an account. So you create a Cosmos account. Underneath the account, you have a database. Underneath the database, you have a container. Underneath the container, you have an item. So think of your relational world. In the relational world, you have a database server, which is synonymous to the account. Underneath the database server, you will have multiple schemas, which you can call databases. And underneath that, you have multiple tables. And within tables, you have multiple rows. So container could be synonymous to the table, and item could be synonymous to a row in the table. So in this resource model, I'll show you in a bit a demo of how Cosmos DB looks like. So at a very high level, Cosmos DB account will be in the form of Cosmos DB name .azure.com, because this is just an account with a key. And underneath, when you are creating your account, you might actually need to make up your mind to choose the appropriate account. Whether if you are doing a brand new development, then I strongly suggest you pick up our core API. If you are performing migrations from Mongo or Cassandra, obviously we'll be choosing Mongo Cassandra API. And if you have graph-like scenarios, then you will be choosing Gremlin with the ability to cross-operate with SQL Core. And then if you have key value storage kind of scenario, you will be choosing the table API at this level. So this is how the screen looks like in the Cosmos DB. As you can see, a subscription underneath Cosmos DB, you underneath your tenant. For example, since I work for Microsoft, Microsoft is my tenant. Underneath Microsoft, I could be part of a subscription. And underneath the subscription, the project I am working on would correspond to a resource group. Underneath the resource group, you create a Cosmos DB with account name. And let's say I chose Core SQL API as shown here. And underneath the API, you see notebooks preview on or off. So we provide you a Jupyter-like notebook experience within Cosmos, wherein you can actually query all your Cosmos collections using our notebooks. And then you choose where your Cosmos DB, which region your Cosmos DB should be under. And the capacity mode is provision throughput or serverless. Like I mentioned, if you choose provision throughput, we guarantee the throughput in form of auto scaling or manual. However, serverless is where you for your dev workloads you can choose the capacity so that we actually determine what your application needs versus you demanding how much throughput you need. And we'll see what are the advantages and disadvantages of either of those approach. Nevertheless, this is how you create the account. Once you create the account, you create a database. Once you create a database, you create containers underneath that database. A container not only contains items, but it contains other components such as store procedures, triggers, user-defined functions, etc. So stored procedure is in your relational database world, whatever you have as a stored procedure that operates on whenever something is being written into the table. You perform a set of tasks, except this stored procedure could be written in a native form in form of JavaScript, and they are extremely fast and complement very well all of your items. And then user-defined functions for your own user-defined criteria that needs to be done, and triggers are also available. So items are nothing but the JSON documents. Why JSON? Uh, because JSON is a open standard document format, which is very popular, and therefore we chose JSON to be our document. And it is language independent. It works on contracts. It looks like key value pairs. It can have arrays as embedded items, and it supports recursion or recursive embedding. And last but not least, this schema is very, very flexible, and therefore we chose JSON documents to be our items. As you can see here, there is a customer, and customer has two attributes, CSID and full name, which are nothing but the key value pairs. And you see an example of array. You have lines and there are two items in the lines. And those two items further contains subcategories in form of key value pairs. And these are the key value pairs themselves. As you can see, we can store numbers, we can store strings, we can store a binary. Now, since we understood what are the various components of a Cosmos DB, let's understand how Cosmos DB performs and what do you need to provide Cosmos DB in order for it to perform, or what is the currency for Cosmos DB? The currency for Cosmos DB are request units. Request units is a rate-based currency. So what does that mean? That means if for an operation you need 10 request units, and if you have 10 request units, you get the response back in the promised read latency or write latency times. Then a request unit abstracts physical resources. That means a resource unit is a function of certain amount of memory, CPU, and IOPS, which you don't need to worry about. And therefore, we define a abstract physical resource into a meaningful user resource, saying that Let's say in order for you to read 1 kilobytes worth of data, you need 1 RU, how much ever memory or CPU or IOPS it is. So RUs are key to multi-tenancy. That means you can store many chunks of data or shards of data if you are from MongoDB world into this storage. You operate across all shards using request units. And they cover all of the activities, right? Whether they are internal processes, customer-facing processes, ETL processes, anything that corresponds to a read or a write is taken care of by RU. Like I said, let's not worry about the physical aspects of a resource unit, but let's worry about the logical aspect of a resource unit, which is very important for us to design this database and design a partition. A request unit is normalized in the sense that one request unit is defined as the ability to read one kilobytes worth of item. So in order to insert 1 kilobyte of item, you might need 2 RUs. In order to upsert, you might need 2 RUs. And in order to perform a query that returns 100 documents back, you need a variable number of RUs. Therefore, by this slide, you understood that RUs are everything in Cosmos world. Since RUs are so important, let's talk about what they are and how they are used. So at the account level, we provision RUs using something called a provision throughput or a serverless. First, let's talk about provision throughput. So a provision throughput says that, hey, I need certain number of RUs per second, right? That's what I said. For example, you can define a throughput, a provision throughput at a database level or a container level. If you define at a container level, then only that container will have that much throughput. But if you define at database level, multiple containers could share the same throughput. As you see here, this is my application, let's say, that uses 4000 RUs per second and then drops all the way to 2500 RUs per second and again go back up all the way to 4000 RUs per second. So in the scenario such as like that, how would we actually perform a provision throughput? Let's see how a provision throughput might look like. A provision throughput is provisioned in terms of RUs per second. A provision throughput can be increased or decreased instantaneously. And it is metered hourly. So for example, let's say you actually increased or immediately, like let's say after 15 minutes, you decreased, right? So after 1 hour, you will change back to your a new item. So it is like for hour, it would be the same, whatever, whether you choose to increase or decrease. If you choose to decrease after increasing, you would be metered hourly. Then the background processes that are performed, such as time to leave expiration. And as you can imagine, the indices that are present on particular collection, all of these background processes might also use some number of RUs. So let's see how actually we can actually design such an application. Let's talk about a manual provision throughput. So given we chose the option of manual provision throughput. What that means is I chose 4000 RUs per second. I have 4000 RUs per second. And if your application is benchmarked at 4000 RUs per second, like so, manual provision throughput is perfect for you because you know the traffic of your application. You know how the traffic is being performed. More or less, when you smooth everything out, it is at 4000 RUs per second, and that is totally fine, right? So most of the production applications we see day to day belong to this category, and they probably are fine. But I would always argue that 24/7, your traffic might not look like that. What if your traffic is light during nights? What if your traffic is light after you close the shop or when your shop is open? That leads to unused capacity. For example, if there is a significant chunk in your traffic wherein your traffic is significantly lower than the defined 4000 RUs per second, it will lead to so much unused capacity in that time, and that unused capacity is lost money. And therefore, in order to solve these kind of cases, manual provision throughput is not the right approach. So this is where we choose an auto scale provision throughput. So an auto scale provision throughput, what it does is it actually creates a higher end for your RUs. Let's say if your application is like so, and let's say the higher end is 4000. The 10% of 4400 RUs are the lower, the minimum. And your traffic oscillates between those two, and we auto scale whatever is needed for your application. And whatever are the costs that you see between these peaks and valleys is all the costs you are saving, because your traffic is always moving between those two lines, the minimum and the maximum. So this is a perfect example of the traffic workload where you have to choose auto scale provision throughput, where you can save a lot of money. Now, let's even say, because remember in auto scale provision throughput, I said 10% of minimum should always be up and running. For this scenario, very infrequently, your traffic is going below 10% or below 400 RUs. This is perfectly fine. We are not wasting any money just because we had minimum 10%. But what if you have a scenario wherein you want to uh, save money, wherein your traffic is significantly below 10% for extremely long period of time? When can such thing occur? Such thing can occur when you are in a development phase, or when your application has very low traffic and the traffic nature is very sporadic, in which case provision throughput might not be the right choice, but you can choose serverless, and we'll come to that. As we mentioned before, database level throughput provisioning. Let's say you provision 10,000 RUs at a database level. And then let's say there are 3 containers. Here, those RUs are being shared like so, depending upon how much is needed at that time. And then there is this concept of mixed throughput provisioning, wherein, for example, for that container, for whatever reason, you give 2000 RUs per second. Henceforth, I won't call RUs per second. I'll just call RUs. So 2000 RUs on one container and 6000 RUs distributed between the two containers. That's called mixed throughput provisioning, which is valid in some cases. You can definitely do that. Then, as we discussed above, what if your traffic is significantly below the 10%, like this? So as you can see here, most of the time your application is idle. If you were to choose auto scaling, your application will be idle for a lot of time, and you end up actually spending money for the 10% minimum, which is highly unnecessary. In this case, I would choose a serverless capacity mode, which is available with us. And in serverless capacity mode, what's going to happen is we won't have the 10% unused capacity that is dedicated in case of auto scaling. But here, whenever the traffic comes, we do that and we just go back, right? Like this. For example, let's say you need 40 RUs here, 20 RUs here, and 40, and so on and so forth. Probably overall you will be consuming 100 RUs throughout the day versus 400 RUs throughout the day. It's just waste of our money, and therefore this is a very economical choice when you have a development workload like this, or users who sporadically come onto your application and do a very lightweight traffic. Usually we recommend doing this for a non-mission critical workload and a development workload. So how do you measure RU charges? And what dictates RU charges? Let's talk about these in a little detail. So the complexity of the query definitely dictates the request units that are consumed. And the number of columns that are created as an index also dictates the number of RUs. So why do indexes dictate the number of RUs? Why? Because in the indexes, if you don't specify an index, in Cosmos, uh, every column would be created as an index. And therefore, system should know or build an inverted index like structure wherein it has to know what values are in which partition and how to read them. So all of those memory operations that it performs for every new item upsert or insert is an index operation. And therefore, you will end up spending RUs on that. So we will see now a demo on how to actually see the query cost. There are many ways of seeing the query cost. Probably the simplest of the ways is if you are performing a query in tools, we actually provide the ability for you to see the request charge then and there. And let's say you are making an API request, you get your request charge underneath an element called XMS request charge within your header. So the number of index terms, like I said, dictates are used to, and I would actually make those columns that are frequently used in your where classes um, as indices, and remove the items which we are not using. So with that, let's go and see our second demo on how we index. So as we have seen thus far, this is a Cosmos DB account, and the Cosmos DB account comes up with a Cosmos DB URI like shown here. And its capacity mode is provision throughput. I chose a provision throughput, and I have many containers underneath my database called Contoso Auto, which is what I used for the application I have showed you. For example, let's go and take a look on any of the collection. For example, the collection or container here is called maintenance. Underneath the maintenance, there will be items. So let it pop up. Awesome. So underneath Contoso Auto, we have the container called maintenance. Underneath that, we have items. And as you can imagine, each item is maintained as a key value pair here. And then you can query the items like so. And for example, let me say, select star from C. And without providing any filters, let me execute this query. And I got, let's say, the 100 items on this page. And let me see the query stats. As you can see, the request charge is 6.73 RUs. Okay. And let's say, instead of this, what I do is, we will actually go into a concept called partition in a little bit. But for now, let's say the partition column on this is win. Let's say we go and query on a win number. So for example, let's say I go and query on this win number. I go back to my query and I say where c dot win is equal to the one I pasted. So now, if I run that query, look at the number of RUs. It is now 2.83 RUs, which is 1/3 of what I got before. And the reason is because I am getting all of this from the same partition. So now let me go and take this one step further and say and include this field called ID, which is the unique identifier of this particular item, and say and c dot ID equal to that one. And now let me run this query. And then I got the request units of 2.93. So what the difference between previously I got from single partition, and within that partition I used ID, and this is called point read. A point read is not only getting from the partition but pointing to a specific item with its unique identifier. So the point read is the best form of read you can get from the database. And as you can see here, within scale in settings, this is the indexing policy. And if I left it at default, for example, the included path is I'm including everything in the indexing. That's not a good practice though. You should not do that. This is a demo, that is fine. You should exclude as much as you can and keep only the items that are needed for performing the indexing. So let's go back to our presentation and see some things we have discussed in action. So partitioning. So what is a partition? A container can contain many partitions. So partition is the mechanism of scale out. For example, let's say you have a partition, and let's say you are storing certain records in that partition. And let's say the partition exceeded its capacity. Then Cosmos automatically spins up a new partition and it exceeds the capacity. Then we do the same, and we do that to infinity. Therefore, the scale out is nothing but scale out is directly proportional to a number of partitions that you have, right? So that's the scale of your database. More the number of partitions, uh, assuming you did your partitioning correctly, then you have scaled out your database to such an extent. There are two kinds of partitions in Cosmos DB. One is a physical partition and another one is a logical partition. A physical partition is a partition wherein we actually provide the physical resources underneath, such as CPUs, memories, IOs, as one machine, and on top of which you define your logical partitions. For example, the win number you have seen in the previous example I have shown is an example of a logical partition. So this is a physical partition, that's a logical partition, and we ensure that all logical partitions fit into a physical partition until the physical partition is full, and then we create a new physical partition, and then more logical partitions sit on that. So now let's see how it works with a concrete example. So these are all the logical partitions. So for example, every physical partition is responsible for a key range of logical partitions. For example, let's say in our case, win number 1, 2, 3 is stored in physical partition 1, whereas win number 110 to 140 are saved in physical partition N, correct? So as the vehicle win number, as the data corresponding to the exceeds the capacity of um, the capacity of uh, uh, the physical partition. For example, let's say here, now the fourth win have to come here. And now this physical partition cannot accommodate the fourth win because this physical partition is now full with the existing three logical partitions and there is no space for the new logical partition. Then what happens? Then we spin up another physical partition. Our example, let's say this is all full and now a brand new item came on this logical partition. Now we have to move this to a new partition. We have to move one of this into the new partition. That's how it works. So the physical partitions keep growing. So keep that in mind. So now everything is stored at a single location. How is that possible? It is possible because we hash out your partition. So we hash out your partition so that we save everything in the same physical location, right? So for example, XYZ999 is always hashed to a same value, and that value always comes and sits in the same place, like shown. And let's say we assign 30,000 RUs on this particular container. If there are 5 physical partitions in this container, each physical partition gets 6,000 RUs. That's how it works. Every physical partition have the same number of RUs as other physical partition. Therefore, you have to divide 30,000 RUs, assuming there are 5 partitions here, everything gets 6,000 RUs. And therefore, choosing a partition key is very, very important. Why is that? The reason is because of hard partitions. For example, instead of saying a VIN number, let's say we partitioned on the state. And let's say I have more vehicles in Texas than I have vehicles in the state of Montana. And let's say all of the Texas data is sitting on the left-hand side. And all of the Montana data is sitting on the right-hand side in a cold partition. So the queries that I'm going to fire on my database will not perform well because of this hard partition issues. Therefore, we need to spread the data as evenly as possible so that we can spread our RUs as evenly as possible. Because remember, I have only 6,000 for this and I have 6,000 for this physical partition. And therefore, when I am always going here, I'm always using this 6,000 and I'm wasting the 6,000 here, I'm wasting 6,000 here because the very sporadically I go and read there. So please keep in mind that you have to evenly spread your document across all the partitions. That means you have to actually choose a proper logical partition key so that when they go and sit into physical partitions, they actually avoid hard partition but they avoid hard partition scenarios. And also, please make sure you choose a key wherein your partition key is immutable. So if you change the VIN number, remember the hash changes, and therefore it has to repartition everything. This is not good. Therefore, when you choose partition, we choose a value wherein it cannot be changed. For example, VIN is a classic example where VIN number cannot change. And also make sure you don't actually have infinite number of values within the partition because there is only, remember, logical partition has a limit. I think it is 20 GB and you cannot cross that. So for example, let's say you are having the data on a single VIN, which is greater than, let's say, 10 gigabytes. You cannot actually, like keep using VIN number as your partition. Probably you might need to add a day to that or a month to that so that, you have just bounded number of items. So the good practice is always choose a key as a partition key wherein the items within that partition are bounded in nature. They cannot be unbounded in nature. Okay. Last but not least, choose a high cardinality, which means a larger range of values versus, like I said, right, instead of choosing a state, it is better to choose VIN number as a partition key. And moreover, we'll be talking about partitions as we go through this journey and how to design our partitions in a better way. So now let's see how partition keys are used for reading. For example, if you actually are performing a CRUD operation, let's say you are making a brand new insert, or let's say you are performing an upsert or whatever, or reading something, right? Let's say you do a get. So you always have to, you cannot actually do a multi-partition query, which is a bad practice. We call it as a fan-out query. A query that is trying to read from many partitions at one shot is called a fan-out query. We always suggest that you create your queries in such a way that they all read from the same partition. Understood that partition key is a very important decision-making entity when you are designing your Cosmos database. So without a proper partitioning key, your read request would be disturbed, your write request would be disturbed. It will lead out to fan-out queries. Also, we spoke a little bit about point reads, which are, whenever you are doing CRUD operations, point read is the best you can do. Therefore, please make a point to include ID along with the partition to get a point read. So these are the single partition queries. Single partition queries are the fastest, right? So AKA, you provide partition key in your where class, and there you go. You manipulate, you operate all the elements within that partition. Then there are these fan-out queries. Fan-out queries are very bad. So fan-out queries are the queries that actually try to read from many partitions. And that's not usually a good thing. We should avoid fan-out queries. So if you are issuing fan-out queries, then I would strongly recommend that you redesign your partition key and try to put all of your data in a newly designed container with a new good partition key. Okay, so we already see the point read. We queried a record, and I will show you the notebook experience in a second. Let's actually, move on to our Contoso logistics and see some of the key attributes, and then we will go back and see some of the experiences. Um, so let's see some of the concepts of design, and we will actually talk a little bit about these in the next session too. For example, let's say we have a trip entity, and in the trip screen, you have actually multiple packages associated with that. So now how would we model such an entity? So in a relational world, you would be tempted to create actually a primary key foreign key relationship wherein you have actually the trip ID and you have actually all these packages in a separate table, and you have a package ID in the trip table, and you want to say trip.package ID equal to package.package ID and hence query. What if we totally avoid that referencing, and what if we get all the packages corresponding to a trip and embed them within one single document? Remember, Cosmos doesn't have schema, therefore we can do that. And by doing so, if we are actually querying the trip, it would be just a single query versus doing it 2 times, which is very good, right? So this is called embedding, okay? Soon I will show you how to embed. For example, this is a trip and that is a package, right? So what if we get that the key attributes of the package, such as package ID, and let's say we are interested about the temperature that is needed for that package, and that's it, right? So let's get those 2 columns here, right? Like shown. So then, last but not least, do we really need, yes, we embedded, but do we need one container for packages, one container for trips, one container for assignments, so on and so forth? No, absolutely not. Remember, we don't have schema. Therefore, we can put all of the entities, namely packages, consignments, summaries, uh, vehicles, and trips all in one place, all in one container. This is called co-locating entities. And this is actually one of the design methodology. For example, this is the trip, this is the package, right? So one of which has entity type equal to trip, one of that has entity type equal to package. That's the that's the thing. And remaining things, right? The partition key is the same. For example, it's a win number. So for that win number, what are all the packages associated? What are all the trips that are associated? Consignments that are associated, right? All of that stuff could be stored in one single entity. And we will see that, right? I will show you in the demo very soon of how we do that. So when we are querying the co-locating entities, now instead of joining multiple tables, all we can say is, hey, get me from this table where entity type is equal to trip, and boom, you got the response back. And not everything in ascending or descending so that you have all that information at one shot. So this is again the example of embedding that is being shown here. Like I said, if you want the bare minimum attributes of the package, such as package ID, its height, length, and width, you just embed it into the trip, and that's all it is. So then let's see all of these together at one shot. So let me cover the last concept in designing. This is called denormalizing the data. So in data denormalizing, you have consignment, you have trip, and you have customer here, and you have consignment there. So what if on the trip you have this consignment ID, but you also get the customer onto this, right? So instead of joining consignment ID to consignment ID, if you were to join consignment ID to consignment ID, then there is the customer, right? So instead of that, what if I denormalize, and what if I get the customer name, just the customer name from the consignment and nothing else onto this, and put it on the trip like that? Now you can always ask me, what if the customer name was in error, and what if someone go to the consignment and change the customer name? For example, they mistyped, and instead of Bellows College, they say Bellows College 1. How will I actually get the same change here? It is possible using something called change feed, which we discuss next week. Given that, for now, take my word that we can actually sync these terms up, and assuming that we sync the things up, I hope you won't have any problem bringing the consignment customer directly onto the trip. Now on the trip, we have all the information in form of co-location, in the form of embedding, in the form of denormalizing, all in one place, so that our screen could be fetched with one single query. Let's see the demo now. Let's see everything what I have described in action. Once we go here, let's see our page. So the idea is, if we go to trips, in the trips, we should be able to see the vehicles, we should be able to see the consignments, and we should be able to view the customer on that consignment and its status. And also you see the number of packages, just the summaries are available here. So that means we needed the package IDs in order to perform this count, right? That's all. And we needed the vehicle VIN number. So that's how we designed the trip, right? So that with one query, we get all of these at one shot. So if we now go back to our Cosmos DB, in order to show you this one in action, let's say this is the maintenance, right? So in this container, for example, I want to actually point you to metadata. Let's say in the metadata, you see the entity type of vehicle here. So you can have an entity type of trip, an entity type of package, and so on and so forth. So let me quickly edit filter, and where I say where C dot entity type equal to C dot entity type equal to trip. Okay, let's see the trip. As you can see here in the trip, we have the VIN number, VIN information. We have actually all the packages that are embedded here in one shot, right? And then Last but not least, we got the very key fields from the consignment, such as the customer name, consignment ID, and delivery due date. Okay, so with this information, right, the bare information that is needed, bare minimum information, all I need for this trip is what is the minimum temperature I need to maintain in my truck for this kind of package. So if I have two refrigeration units, I distribute these into two different refrigeration units and then track that as a real-time telemetry. At the same time, I also want what is the current status. It's still in pending, right? Which will be updated. Also, I need what is the VIN number because this is our partition key. And now I also need which customer is this consignment going to and what's the delivery. With that, now I hope you understood with one single query and with one single document, if I am able to design, I should be able to pull the screen up like this at one shot. For example, if I want everything for this VIN number, right? These are all the trip details. These are all everything that is ever needed for me on one single screen. So, and that is going to consume lot less RUs than you doing queries on different kinds of entities here. So we will actually expand a little bit greater detail next week on how we can do some advanced querying, etc. in the Cosmos. But for now, I think you are convinced probably by now that the three things such as co-location in action, you have seen the embedding in form of packages and the denormalization in terms of consignment customer. All of these three concepts are very, very important in a NoSQL design scenario. So moving on, let's actually wrap today's session up with some of the key items around when we need to co-locate, when we cannot co-locate, when we cannot embed. So, so when we co-locate, when actually we need all the items, for example, corresponding to a VIN. For example, let's say instead of going to two containers and fetching two different data sets and perform something in the memory of your application, if I were to put everything in one single container, and if all of them belong to same logical partition, for example, a trip belongs to a vehicle, and a vehicle belongs to a vehicle, and a consignments belong to a trip. So all of these are related to each other in form of VIN. And if such a logical partition value or a partition key exists that could avoid multiple containers, it is better to co-locate. And also in why not embed, instead of, within the same container, instead of going to container two different times, if you need bare minimum information, and if it is a small subset or a bounded subset of values, in this case packages, you cannot have million packages for a vehicle. You can probably have like 200, 300, 400 for that trip. And let's say if you can accommodate all of those for that trip in as part of embedding, you should. And the denormalization is same, right? So this brings us to the end of today's session. So in today's session, we have seen some very important techniques such as partitioning. Why partitioning is important in order to achieve the scale that we want to achieve, whether it is 10 gigabytes or whether it is 10 petabytes. Partitioning is the one that dictates everything. And then in the denormalization, I touched a little bit, but there is this concept called change feed, which we spend half of the next session on. A change feed is something, as something changes in the Cosmos DB, the microservices can pick up and then send those changes to downstream. For example, like I said, if let's say you have a collection called customers, in a customer name changed in customer collection, and if you want to propagate that change to many other containers, change feed will come in handy. And there is this concept called analytical store in Cosmos, which we will discuss for especially for doing analytical operations in SQL data warehouse world. And then we actually speak about other APIs such as MongoDB and Cassandra at a greater detail in upcoming sessions. Meanwhile, if you want to actually practice the NoSQL demo that I have shown, especially the Contoso logistics, we have actually, as part of the link that is embedded in this presentation, you can go to the link and you can actually go in greater detail and start learning about this architecture. So today, don't pay attention on to the subsequent architecture wherein we actually do a lot of analytics. We implement microservices using change feed. Those are for the coming 2 sessions. But for today, I hope you were able to appreciate the NoSQLness of Cosmos DB and the partitions that are implemented in Cosmos DB and some of the design techniques such as embedding, collocation, embedding, collocation, and denormalization we have performed within Cosmos DB. And also the GitHub link that is provided here will provide you the ability to go and clone the code and actually there are step-by-step instructions for you to build the application, the Contoso logistics application, wherein you can actually play with the code and see how Cosmos works with the overall ensemble. With that, thank you very much for spending an hour and a half, and we will actually deal with change feed and other techniques in the next session. And I hope you join me over there and learn a little bit more about change feed. Thank you and bye.
Thanks so much, Sri. That was a great delivery.